stage of stellar evolution is our sun in right now? Just put your answers in the chat. Yeah, I see two answers. There should be two more. Actually, no, there should be one more. Sahith. Okay. Okay, so yes, it is the main sequence. So the second question I have is, if our sun were at the end of its life right now, or like if we zoom or if we fast forward to the end of the sun's life and it was supernova, what body will be left behind from the supernova? Yeah, I have one answer. Two answers. Three answers. Okay. Here. So yes, it's a white dwarf. We all since you all got it, I'm assuming there's no questions for it. Okay, so the third question is a difficult one. This is the kind of difficulty you'd see in a question on an actual Reach for the Stars test. So get ready. This is gonna be this is the kind of stuff you should have in your notes. So we all know that protostars are pre-main sequence, so they cannot undergo nuclear fusion. So how do they get their energy? And the second part of the question is, what is the protostar composed of? So if anyone knows it, then they can put it. If no one knows it, it's fine. But you should have taken really good notes on each of the stages from last week. I gave you 2 weeks to do that. Yeah, I have one guess. Everyone, if you saw this on a test, you should at least guess if you don't know the answer.
Can you please repeat the question?
So, what is a protostar composed of? Like, what's it made of? And protostars don't undergo nuclear fusion, so how do they get energy? Okay, not. I'll just go to the answer key. So I deleted this question slide, but here's the answer key. So for the third one, the main source of energy of a protostar is the conversion of the gravitational potential energy of the falling stellar mass into kinetic energy. So it's kind of gravitational collapse. So if you got that, good job. If you search that off, bad job. And um and it what it's made of is it's a dense region of it's a dense region of a molecular cloud, so it's in the center of the molecular cloud, and it's mostly made of hydrogen and helium in its core. So it has those elements, but it isn't massive enough to undergo the fusion, as I explained last week. So, any questions, or can I move on? No questions? Yeah. Okay. Okay, so now we'll be going over the types of supernovae. So first, let's go over what they are. You should know these. They're events where a star explodes, destroying itself and releasing enormous amounts of energy. So this has a lot of energy in it. So much energy that if in a galaxy one star goes supernova, it'll outshine the galaxy for the moments of the supernova. Like outshining the whole galaxy with one supernova from one small star or one star. So that's really interesting. And there's a couple types, so we'll be drawing over that. Oh, and if you have any questions throughout the uh, meeting, you could just raise your hand. So the first type is type 1A. So these are taught by white dwarfs when they gain too much mass. They occur most often in binary systems when the white dwarf pulls enough mass off its companion red giant or just companion white dwarf to be able to grow supernova, or when there are two white dwarfs that collide. The white dwarf grows supernova because it exceeds the Chandrasekhar limit of 1.4 solar masses. So if a white dwarf gets the mass of 1.4 solar masses, it'll grow supernova. So this is a much brighter supernova than the type 2 supernova because 1A supernovas are different from the other type 1 supernovas. Okay, wait. So this is brighter than a type 2. They're different from the others because of their absorption lines in their spectra. Do you guys know what they are? Absorption lines. You want me to go over them? No, okay. Um, Here, I'll pull up an image online. So there's three types of uh lines in the spectrum. There's just the whole spectrum. Here, I'll 1 second, I'll find a good image for this. Okay, so share my screen. Uh, Three times. Um, Here. So there's the continuous spectrum, which is the whole spectrum, the absorption spectrum, which moves the emission lines, and then the emission spectrum. So here, I should have made a slide for this. This is my bad, sorry. But here, the continuous spectrum is if you get the light directly from the object. The emission spectrum is if there's it shows the colored lines of light emitted once it passes through an object, and or once it so it shows colored lines of light emitted by the glowing gas. So it the light comes here, and then the gas. Oops, I didn't mean to do that. So the light comes to the gas, but it doesn't come. That's not what we see. We see the gas glow because of the light. And the absorption spectrum is the light when it passes through the gas. So the emission spectrum is kind of indirect light. Do you guys understand? Af- you guys should take
Kinda.
kind of. Okay. So make sure to take notes of this in the future. Um Oh, and I forgot one thing. Did you guys do your homework? I forgot that you write it as homework. You're supposed to take notes on all your DSOs. Did
My
any of
my
you do that?
my partner took notes on 5 of the DSOs. She still has to do the rest. I'm
Alright.
doing the Stellar Revolution, and my partner's doing the DSOs. So yeah.
So make sure to get those DSOs done before invitationals because that's the uh biggest that's a huge portion of the test. Wait, who's your partner again? Are you two partners?
No, Natalia is my partner.
Okay.
My partner is Sritran.
Okay.
So I
Yeah, we
did
took our
like
notes.
I received a email from Natalie about like she couldn't find the specific wavelength for the DSOs. Was that like a problem for any of you guys? Or like the light spectrums? Cause like if you guys didn't have a problem about it specifically, then it's fine. But if you guys do, then like just ask us, and then we'll give resources. Ideally on Teams, but like it's fine. But if no one else had a problem on the that part of the DSL specifically, then that should be fine.
Okay. So no one responded. Should I just keep going? I'll just draw. Presentation. Okay, you'll see the presentation, right? Okay, so yeah, so they have so type 1A supernovas have different absorption lines than the type 1B and 1C, so that's why they're different. But these are the more common of the type 1s. And yeah, these supernovas are always the same brightness. So, but their brightness changes by distance, obviously, but they're always the same brightness because the limit always stays the same. So the white dwarf or supernova will always be of the same mass, right? So they always have the same brightness. So because of that, it's possible to calculate distances of a star near Earth. So we can find the distance of the white dwarf, and that helps us find the distance to stars close to it as well. So yeah, so this is one of the things that helped astronomers believe that our universe is expanding and accelerating in its expansion. So it's a pretty big discovery. Okay, so now type 2. I'm just come back to the type 1B and 1Cs, and you'll see why. So these are the times I mentioned in stellar evolution. These occur when a star of at least 8 solar masses gains so much mass that the continued formation of iron from nuclear fusion, the core implodes on itself. So I went over this, I believe. Uh, when the star exhausts its helium, the gravity wins and squeezes the star tighter than ever before. The core burns hotter and quicker, while the outer layers of the star swell up to hundreds of times the original size, fusing heavier and heavier elements. That's the red giant phase. Or, well, red. This type 2 is specifically for uh, massive stars. So they go into red supergiant phases. And then the core basically gets crushed by this enormous star around it. It implodes on itself and goes supernova. So these are type 2s. They end up in either neutron stars or black holes. Okay, now the type 1B and 1C. So these are interesting. So these occur from the same collapsing core as type 2, but they come from stars that lose their hydrogen envelopes. In essence, a star has layers in it and outside it. So one of the layers outside it is a layer of hydrogen, hydrogen gas surrounding the star. There's a layer of that, and then unlike the 1A, these 1B and 1Cs lose that hydrogen envelope, and oops, and then that that envelope is drawn in their supernova. So that's what makes them different from the type 1As. In the type 1C supernovas, even the helium envelope outside the star is lost. So yeah, if you don't understand this stuff, on YouTube there's really nice videos that explain this stuff. That's how I learned almost everything here. So look at YouTube for this stuff if something seems confusing, especially for the equations. astrophysics equations. We'll get to at some point. So next we'll be going over the types of stellar explosions. So there's a nova, which is when the star flares up and returns to normal, but it peaks at really high luminosities. This often happens when a star is near the end of its life. A supernova, you should know what we've done a bit on that now. So it's when it implodes on itself. It can action a galaxy for a brief period. These events are one time and destroy the star. White dwarf supernovae or described in previous slides. A hypernova uh, is interesting. So it's an extreme version of a supernova that is 5 to 50 times more powerful than a. Wait, one sec. Okay, so I'm sorry, there was a slight disruptance to the meeting. I was on the hypernova, right? So yeah, they're 5 to 50 times more powerful than a supernova. They release 100 times the energy in a supernova and produce gamma ray and X-ray bursts, which you can research. And a kilonova, so when two compact objects collide, neutron stars and black holes. So either two neutron stars, two black holes, or a neutron star and black hole collide. These are not as bright as a supernova, but they release a lot of gamma rays and can produce really heavy metals. So I think I explained this.
So
in
wait,
the last
what's the difference between a hypernova and a supernova?
A hypernova is just a
I mean a
really
kilonova. I mean a kilonova. Like a difference between a hypernova and a kilonova.
a hypernova. A hypernova is a powerful supernova, and a kilonova happens when black holes and neutron stars are related and they collide. But a supernova doesn't have supernovas and kilonovas are completely different. Do you see the difference or understand it?
Yes.
Wait, do you did I answer your question?
Yes.
Okay. So yeah, I think that's all. So I think I touched on how heavy metals get produced. In essence, the heaviest metal you can create, like just in like a normal practical world where stars living, is iron. Stars produce up to iron, which is in the very, very center of its core. It's a really, really heavy metal. To get any metal heavier than that, so you all have seen the periodic table, right? Yeah, I'm assuming you have. Iron is somewhere in the middle of that. So it's like it's not even close to the heaviest element there is. So to get heavier elements than iron, you need extreme conditions. Like a supernova might be one. A hypernova would be a good one. Basically, to create heavier metals than iron, you need really extreme conditions with lots of energy. So yeah, if you don't understand, uh, you can ask me or you can look at YouTube videos. YouTube tutorials are really nice, as I said earlier. Okay, so now I'll go over the star classification systems. So I'll be going over the Harvard and Yerkes. I don't know how to pronounce Yerkes, but it's probably something like that. Yerkes. And yeah, so there's probably other ones, but these are the common ones. I haven't seen any others on a test, so they aren't really important. The Harvard system, It categorizes stars by their temperatures in the following order. It goes O, B, A, F, G, K, M for stars. And you can see temperatures listed. You can see colors and hydrogen contents, and the LTY are brown dwarfs. They aren't actual stars. So the actual system is O through L or O through M, which are stars, M being the red dwarfs, O being the blue hypergiants, and then LTY are what brown dwarfs, which aren't actual stars. I think I went over them. So our sun is a G-type star. And so there's an acronym for this. I didn't know it at first, but then I saw it on a test for each of the stars at invitationals, I think. So then I have to add it now. It's a little weird. So the acronym is O. Uh, oh, I oops. Um, that's it. You can read it. I think it's O. Be a fine, uh, girl. Okay, I'm not saying the whole thing, but that's an acronym. You'd need it in your notes because it came on a test once for me. So yeah. So yeah, LTY are brown dwarfs, L being the hotter ones, Y being the cool ones. And then the updated version is the modern Keenan system, which adds luminosity. So you might want to have a couple notes on that as well. Then
Wait a minute. Can you like go back? Wait. So what does like the what does LTY exactly mean? Like I know they're brown dwarfs, but what exactly like are brown dwarfs?
So brown dwarfs are you can think of them as failed stars. They're massive, but they're not massive enough to go through nuclear fusion.
Oh, and then what's the miscellaneous note section which you've like written in the slide?
Oh, it's sorry. That's so I actually took some of this stuff from my astronomy notes and reached for the stars notes from last year. So I forgot to remove these tiny things. So in my notes, I kind of uh categorized stuff into a few things. I have DSOs in a place. I have stellar evolution in a place. I have a miscellaneous section, a telescope section. I have a bunch of random sections. So yeah, this isn't relevant to you. Yeah. So I'll move on. So this is the other system. This one's used a lot less, but it's still decently common. So this classifies by a star's luminosity. So uh um yeah, you can read through it. So it goes to 5, 0 being the crazy ones, the extreme ones, and then 5 being the main sequence. 500 or D is or I mean just 500, you could say 500 is for white dwarfs because they also have a decent luminosity. I mean it's kind of just in it. I don't really remember why it's in the system, but you can look into that if you want. So our sun is in the main sequence uh section, so it'll be designation 5. And then ignore the Roman numerals part because you can just write it as 0, 1A because usually this is written with Roman numerals. Uh, the 1, the 2, that all of the numbers are in Roman numerals. So that's why I have the conversion. But I think most of you probably know your Roman numerals, so I think you'll be fine.
I know like up till 15.
All you need to know is 0 through 5, and then 500, or just put a conversion table, or just do it the way I did it. Because on a test, I don't think they'll give you Roman numerals. So now we get to the big one, the Hertzsprung-Russell diagram. So this relates absolute magnitudes, luminosities with spectral types and temperatures. Um, Even though some diagrams like this may not have a characteristic like color index, they all have the same shape. The main sequence is the band of stars in the middle and contains the majority of stars. Giants are found above the main sequence, and white dwarfs have their own section in the lower left area. Because each of the types of stars occupy their own regions, goes to show how a star's age changes, or how a star ages, its physical properties change. So just take a moment to take it all in. So because of this aging property, um, the diagram can also be used to predict the location of a new star based on some observations of it. Like if we know if a star has a temperature of 10,000 Kelvin, and the star is in its main sequence, we can find the luminosity of the star. In this case, between 100 and 1,000 solar luminosities. The axes of the diagram are like the luminosity of the star, often in relation to the sun, to the and to the temperature of the star. The temperature in this case is represented by not only Kelvin, should say Kelvin, and but also by the spectral class. So this one kind of mixes with the Harvard. You can see how they connect. So this is one of the big things they'll ask you on tests. So often they even give you the Hertzsprung Russell. Often they even give you the Hertzsprung Russell diagram. But have you guys been seeing my screen?
Yeah, I can see it.
You, st- you still
Ye-
can?
Yeah, I can see it.
Okay, the red line like went away. That sounds it. Okay, so does anyone have any questions on this?
Oh.
Wait, I'm sorry, I misclicked the button. Wait, I'll reopen the thing. Wait, did anyone have any questions?
No.
No? Okay, so on the test, they might view a Hertzsprung Russell diagram and they might have a few questions on it. So this is a really important one. Uh, mm, okay, so I just put a chart of stellar evolution in my notes in case I ever forget something. So, I mean, that basically is everything. Kind of just shows the kind of stuff that happens. Anyone have any questions on this slide or anything? No, no questions?
Yeah. No.
Okay, well then, make sure you get your DSO notes done. Make sure you take notes on the things from this week's lesson and last, or the first lesson and this lesson I just gave. So your invitationals is like, I think next weekend, right? So
Yeah.
you need your DSO notes done by then. That's like the main thing. So yeah, that's all. Okay, bye.
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 Bye.